Hey everyone, Amin here with AI Plays. Today we're covering the noise filter for Luma. Let's get started. To recap, so far we've covered how a camera converts light into a Bayer domain image, how to correct dead pixels, how to compensate for black levels, how to adjust for lens shading, what an anti-aliasing filter is and how to apply one, how to apply auto-white balance gain control, how to convert the Bayer domain image into a full RGB image, how to adjust the lightness scale to make a more visible image, how to convert color spaces from RGB to YCBCR, how to apply a noise filter to chroma channels, and finally, how to adjust the hue and saturation of an image. In video 5 on the anti-aliasing filter, we went into depth on what a filter is and how it is applied to an image. For a brief review, filters are mathematical expressions applied to images generally on a pixel-by-pixel basis. They're used for various purposes, such as enhancing, modifying, detecting, or extracting certain features like edges. We apply filters using convolution techniques by mapping a kernel of set size, say 3x3, on each pixel and applying the specified transformation. Similar to how the noise filter for chroma was applied to the CR and CB channels to reduce the amount of color noise in the image, the noise filter for Luma is going to be applied to the Luma channel to reduce the amount of shape noise in the image. The noise filter for Luma is especially important for two main reasons. First, although the human eye is not too sensitive to minute changes in color, we are very sensitive to changes in lightness and shape. Noise in the Luma channel typically manifests as random variations in brightness across the image, especially in areas with low light. Visibly, this looks like random little specks or grains appearing in the image, which can be very distracting. The most common and recognizable type of luminance noise is called salt and pepper noise, which features sprinkles of white and black dots across the surface of the image. This is an example of salt and pepper noise, and you can clearly tell that even though the noisy spots are very small, they still distract from the real image. The other main factor that makes the noise filter for Luma especially important is for its role in image compression. Noise is essentially high-frequency content, and most compression algorithms work by discarding or reducing high-frequency data that the human eye won't easily notice. This is called lossy compression, since it intentionally loses some data that is deemed unnecessary to reconstructing the image in exchange for compressing the image for storage. By filtering out noise before compression, the image becomes more easily compressible without significantly impacting perceived image quality. So how do we address Luma noise? The simplest and often most effective technique used in cameras is called the median filter. We'll use this 5x5 section of a Luma channel with pixels labeled P0 to P24 and a 3x3 median filter as an example. The filter will start on the pixel P7, covering the top left 3x3 section of our 5x5 snippet of the image. The median filter, just like all the other ones we have used in the series so far, is applied to the image on a pixel-by-pixel basis using convolution techniques and a kernel. What makes this filter unique, however, is that we're not applying mathematical operations or summing over the extracted portion of the image. Instead, we extract the 3x3 section highlighted by the filter, identify the median value of the 9 values, and store the median value as the new value of P7 in a copy of the image. As usual, we never modify the original image during the application of the filter. As a side note, filters are generally classified as linear or nonlinear depending on whether they apply mathematical operations or not. Since we're not applying mathematical operations like addition or subtraction, the median filter is a nonlinear filter. Now we've covered what a median filter is and how to apply one, but we have not yet covered why they work. What makes them so effective lies in the fact that Luma noise presents itself as random point variations in the image. These point variations, like in salt and pepper noise, generally hold extreme values relative to the rest of the image, or even the surroundings. The median is the center value, not the average value, so it's able to completely ignore the effects of extreme values in the image. And that's exactly what the goal of the noise filter for Luma was, to smoothen out the image and get rid of extreme values. But that leaves us with one problem. If the median filter ignores extreme values and smoothens out the image, what about edges? Does the median filter ruin the edges of the image? And the answer to that is actually no. Let's come back to the 5x5 snippet of the image example, but this time assume there is an edge right here on the P4 column. So the image is totally white to the left of the P4 column and totally black to the right of the P4 column. When the median filter is on pixel P3, 6 of the 9 pixels in the filter are full white, so the median value is full white, and no harm is done. When the filter moves over 1 and reaches pixel P4, now 6 of the pixels are full black, and so the median value is also full black. You can do this exercise with different directions and different scenarios, but the end result is pretty much the same. The median filter does little to no damage to the edges of our image, which makes it ideal to smoothen out our image. Now let's have a look at the code. As you can imagine, the code is actually incredibly simple, and it's practically a copy-paste from previous models. We start off by defining the NFL function, which takes as input the pure luminance Y channel from all the way back in video 9, color space conversion. The output is NFLY, the luminance channel after applying the NFL function. To start, we change the data type to uint16, mostly just as a good practice. Since we're not running any real math calculations and there is no threat of getting values greater than the established maximum value in the image, this isn't really necessary for this step. Next, we make a copy of the image on which to save the filter results, extract the rows and columns to iterate over, and pad the image. Finally, we start on the main loop, which is really just applying np.median on 3x3 sections of the image, which are extracted using the same numpy slicing from previous steps. This is the resulting image after applying the noise filter for Luma. As you can see, there's not much change, just a little bit of smoothing out for the top black bar that looks like a cover for the color checker. This is about as expected, since again, the image we're using in this series was quite high quality to begin with. That's it for today, everyone. Next time, we'll cover the edge enhancement filter. Have a good day.